Andreas Weis has been writing C++ in many different domains, from real-time graphics through distributed applications to embedded systems. His current focus is on writing software for safety-critical systems, in particular in the context of automotive software. He's an active member of ISO C++ committee and the MISRA C++ working group. Andreas is also one of the co-organizers of the Munich C++ user group. Fun fact about Andreas is that his favorite comic book character is Scrooge McDuck. I think that we can share this opinion with him because I think that we also want to swim in the gold pool like Scrooge McDuck used to do. Okay, so the title of the lecture is Deciphering C++ Coroutines, Mastering Asynchronous Control Flow. Andreas, the stage is yours. Big applause for Andreas.
Thanks. This is Deciphering Coroutines. This is me. You can find me in various places on the web and also contact me via email. And you noticed on the title slide there was a part 2, because I was already here at this conference 2 years ago with a talk called Deciphering Coroutines. This talk assumes familiarity with the contents of part 1. So in particular, it assumes that you know the basics of the coroutine language mechanism. We'll do a very quick recap of part 1 now, but it will be very brief, so hang on tight. So a coroutine is essentially a function that can be paused in the middle of the function body, and then you can resume it later with all of the surrounding state of the function still intact. And there's really 3 major components of the language mechanism that you need to know about. The first is the return type. This is just the return type of the coroutine function that you see in the signature. This is a user-defined type. And it defines the interface through which the outside world can interact with the coroutine. And since it's a user-defined type, you have pretty great flexibility what you put there in the interface and how you make that look like. The language really doesn't restrict you a lot there. And one of the goals of this talk is to help you a little bit better to understand what a sensible interface could look like there. So a simple example that you could have is you have a coroutine here, and then the return type of this is what we're talking about here. And you will notice by just looking at the function, you have no way of telling whether this is actually a coroutine or just a normal function. You can't tell this from the outside. And that's an important aspect of the feature. So the best way to think about this is that the first call to a coroutine function is like calling a factory function that produces the return type. It does not necessarily execute anything of the implementation of that coroutine, but it for sure will fulfill that duty of creating that return type. So since C++23, we actually have one of those return types in the standard library. That's the state generator, and this allows us to yield values from the middle of the function, like we do here, in the middle of the loop. This generator implements the range concept, so anything that works with ranges can consume the values from the generator, like we do here with the range-based for loop. You can also pass it to ranges algorithms or anything else that you could do with ranges. If you don't really see how this is useful to be able to do this co-yield from the middle of a loop, try implementing an iterator that traverses a complex data structure like a tree or a graph. Like start out by just writing the loop that just prints the element, and then try to refactor that into an iterator, and you will see that this is surprisingly difficult. And with coroutines, this allows you to write like the most simple form of that code. So it doesn't really increase the expressive power of the language, but it makes it much easier to write certain things down. If you go back to part 1, it showed you actually everything that you need to write such a generator yourself. The second part of the mechanism is the promise type. So while the return type determines the user-facing interface, the promise is part of the compiler-facing interface. So it provides means for customizing the behavior that is invoked during startup and shutting down of the coroutine. This is what it looks like. So unlike the return type, which we can implement pretty much whatever we want, here the standard specifies a set of functions that we need to implement. And then those functions will get called by the compiler, so by the language mechanism as the coroutines goes through the phases of execution. And these are not functions that we call from user code, right? These are being called by the language mechanism, which makes them a bit special. The final part is the awaitable. The awaitable is a type that we can use as an argument to the operator co-await. So the operator co-await is the operator that we call whenever we want to suspend a function. And the argument to that operator is of type, of an awaitable type. And like the promise, this is also a compiler-facing interface. So again, there's 3 functions that are specified here, which we can implement ourselves to customize what will go on whenever the coroutine machinery reaches a certain part of the execution. And in particular, this customizes what happens before suspension and after resuming a previously suspended coroutine. And then we also saw in part 1 how all of these facilities are connected, and we built up this little cheat sheet that we can use to reason about like how data flows here. If you haven't seen this before, notice in particular the promise at the bottom here, which has sort of a central position that holds the different worlds of the caller side code and the coroutine internals together, and we can use that object to exchange data between the two. If you're familiar with the cheat sheet and you want to use it to follow along, here's a QR code where you can get it. I will leave this up for a couple of seconds. But I want to talk very briefly about like why I'm now back with a part 2 after 2 years. So at the end of the last talk, I said, you now understand all of the boring parts of coroutines, and now you can actually start doing something interesting, but I didn't have time to cover any of the interesting stuff. So this talk is about one of the interesting use cases, more interesting than just a generator, and one that is of particular prominence, namely asynchronous computation. So in other languages like C#, Python, JavaScript, Rust, they all have dedicated language features for this, and they typically use this pair of keywords, async and await. And we will see in this talk how we can implement with the C++ coroutines something that brings us very close to what we have in those languages through those keywords. But we will also see like some of the differences, how C++ does things differently. If you're like most people and don't really understand what is the deal behind coroutines, why you would want to use them in the first place. Andre gave a great talk last year here that focuses exclusively on motivating coroutines, specifically for this use case of asynchronous I/O. It's a great talk. Watch it. I will not be covering any motivation here since we're already short on time as it is. A few words of caution before we dive in deeper. I will at times lead you astray. Please don't get confused by this. Hopefully this will only help deepen your insight whenever that happens. I will not be covering multi-threading since that's its own can of worms. And this is not a best practices talk. Like this is everything you will see here is pretty much slide code. Please don't copy this into a library for general use. All right. Let's start by building a mental model for what we're trying to do here. So our scenario is we want to execute some complex task, right? So we have some function that spawns up this task, and then we have an outer function that computes like some partial results depending on what is provided by this middle function. This middle function in turn also depends on another result from an inner function. And now in this inner function, we have this blocking I/O call, right? That is just needs to do some I/O, and that could just take a long time in which we cannot really do anything except wait for the I/O to come back, right? So while we're in there and waiting, like really none of these functions can do anything sensible, right? Since they all depend on this I/O result to come back before they can continue execution. But main is now also blocked, but main actually may be able to do something useful in the meantime, right? Spawn another task that carries out an unrelated branch of computation. So what if we could just suspend those functions over there while we're waiting and then do something useful in the meantime? That's the main idea here. So a straightforward solution to that is just use threads, right? Just spawn all of these tasks in their own thread. So they go ahead to the side and they run in parallel to main. And then while the inner function is waiting for the result, main can in the meantime just do other things. Of course, threads have a bunch of problems. Thread creation is quite CPU intensive. It's also memory intensive. Thread switching is also expensive, right? If you have a context switch like between main and worker threads, you need to pay for that. The blocked threads, even though they're not blocking main, they may still consume CPU cycles. And depending on how your operating system implements this might be a non-trivial overhead, especially if you have a large number of threads. Once you have threads, you need to think about synchronizing access to shared data. And if you've ever done multi-threaded programming, you know how hard this is. And there's more problems, right? So this is a solution, but it's not an ideal solution. And in particular, it's not a solution that scales well, right? Like this might work well if you just have 1 or 2 worker threads, but the more threads you have, the more difficult these things become. So one alternative to threads that is often mentioned is these so-called green threads, sometimes also known as fibers, user mode threads, cooperative multi-threading, and also stackful coroutines. So how does it work here? So instead of spawning a thread, we're spawning a green thread. And then in the inner function, we now split our blocking I/O call up into 2 parts. So we start with a setup that just sets up our I/O request. But then instead of waiting for the result to come back, we suspend at that point. And we want to be woken up once the result becomes available. So the way that this looks like is when we spawn the green thread, this thread is spawned on the side, our task stack is being built up there. Then we reach this suspend call, and at that point we switch context over to the main thread. The main thread now returns from the spawn function and can do other stuff in the meantime. Eventually our result comes back. Main will invoke some sort of completion handler, and that will then in turn suspend main, and again hand control back to our green thread that was waiting for the result. And now our inner function can continue executing. So this looks somewhat similar to what we've seen with the threads before, but green threads, because they don't involve a context switch that requires help from the operating system, they can be executed with much less overhead. There's no synchronization needed since we don't have anything actually running in parallel. Everything runs sequentially. But the threads need to cooperatively decide when to give up control and hand over to another green thread. However, the intuition about control flow is still very similar to threads. So if you already know how to program with threads, then programming with green threads is like similar intuition. It's just a little bit easier than before because you don't have these threads running in parallel. So how can we implement something like this with C++ coroutines? So the biggest difference here is that C++20 coroutines are stackless. And that means we can only suspend one function at a time, right? Whenever I suspend from a coroutine, control goes back either to my immediate caller or to whoever was resuming that coroutine. So if we want to suspend a computation that is spanning multiple functions, we need to suspend them all one by one. And that's really the goal of this talk, right? We want to figure out how we can suspend an execution context that is larger than a single function. That's the one thing that this talk is about. Okay, so let's try and do this. Okay, starting from our blocking IO call that we have. We want to introduce coroutines. So the first thing that we do is we sprinkle the coroutine keywords in there. And then we now also need to change the return type to be a coroutine return type. I call this one async here for the purpose of this talk. You will often see these return types named something like task. Recently, also people started to favor lazy as a name for this. I call it async here because of the symmetry with async await in other languages. But there is a design space for how these types look like. So be aware of that. But really, at this level, there's nothing more to do. Like there's some magic going on there inside the async IO call that I don't want to go into at this point, but that's pretty much what happens at the innermost level. Now, at the middle function level, again, the same thing, right? We sprinkle the coroutine keywords in there, and we have to change the return type. But now, something interesting happens. If we look at the first line of the body of the middle function and we pull that apart, we will see, okay, what's actually happening there is we're calling the inner function. This is like we said before, like a factory function that gives us back the async IO result, and then we co-await on that. So what we see here now is we have the async type in two different roles. We have this once in the role of the return type and once in the role of the awaitable. And we didn't have that before. So the async now has a dual interface. And understanding that is one of the key insights here to how the mechanism works for async IO. So let's look at what happens when we want to suspend nested tasks. So we have adjusted all of our interfaces, and now let's say we're in main, we want to spawn up all of our tasks, right? So we spawn up our stack of functions, we reach the inner function, and now it reaches the point where it's waiting for the IO. So we want to suspend it and drop it off the stack, right? And we really want to do this with all of the outer functions as well until we get back to main. Main now is free to do other stuff in the meantime, and then eventually when we have the result, we want to resume the computation, we want to resume the called stack to its initial state, right? That will be the simple intuition if you come from green threads. So let's zoom in a little bit. Let's see how that works in detail. So we're here in the outer function, right? We get the awaitable back. Then we call co-await here. Okay, everything's fine. Await suspend on the awaitable is called, and now the function goes into suspension. Now, things happen in the background. Eventually, we're woken up. The outer function can continue execution. Await resume is called. We're back in the outer function, and yeah, this is actually not what we wanted, right? So we didn't want to continue execution of the outer function, right? When the IO result is available, where we want to continue executing is in the inner function, because that was the one that was waiting for the IO result. So this is actually not going to work. And this is the first important lesson here. Resuming suspended coroutines from the outside in does not work. And the reason for this is once a coroutine has been resumed, it cannot be suspended again, unless we also call co-await again. But we do not know from the outside how often we need to do this, because we don't know what's going on inside this inner function, right? This could need like 100 IO requests before it has finished, and we can't just keep calling co-await. So the intuition here should always be, if I co-await such an async function, what I want that to mean is wake me up once that function has completed all the way through and its final result is available. Switching gears here for a bit. What's a call stack anyway, right? So we have kind of this problem now that we need to suspend and resume these functions one by one. So we're sort of doing what the call stack is doing in sequential execution. So it might be worth taking a closer look here. So in memory, right, we have this region of memory that holds all of the things that are relevant to the execution of our function. And then we have these three registers, a stack pointer, a base pointer, which is often also called the frame pointer, and the instruction pointer. So the base pointer and the stack pointer, they mark the range of memory in which the state of our function resides, right? And then the stack grows as we accumulate like more local variables to the function. And below the base pointer, we have stored on the stack the frame pointer and the instruction pointer of the function that called us, right? And this is important because once our function has finished executing, we need to know where to jump next in memory to continue execution with the surrounding function, and we also need to be able to restore the state of that function. So one way to think about this, what is happening here in memory, is that we really have a linked list of stack frames, right? And we can follow them by going like from the base pointer and then like through the individual stack frames in memory, from jumping from frame pointer to frame pointer. So this is a singly linked list of stack frames with links pointing from callee to caller, right? So inner functions point to outer functions. And because we can traverse this list in memory, we can always hand control from inner functions to outer functions. So we will need to do something similar to this. So from now on, I will use a color convention here to make things a little bit more transparent to figure out. Whenever you see something marked with the indigo color, as on the top, that's the inner function. Whenever you see something marked with the orange color, that's the outer function for the context that we're talking about. So indigo, inner function, orange, outer function. So if we look now at the async object and the two roles that it plays, then we see that in the context of the inner function, the async plays the role of the return object. And in the context of the outer function, the orange function here, it's playing the role of the awaitable, but it's the same object, right? So the object that is returned from the call to the inner function acts as the awaitable in the context of the outer function. So to clear this up a little bit, let's look at the two roles in isolation first, and then let's see how it comes together. So the return object part is the easier of the one, especially if you're familiar with the things that we talked about in the last talk 2 years ago. So the return object, we will put in there a coroutine handle that points to the inner coroutine. And we will use the constructor of the return object to populate that handle. And that's really all that's going on here, right? So this constructor will get invoked through the promise by a mechanism that is largely driven by the language. You don't need any user code to end up in this constructor, and you will get passed by that language mechanism this handle, and we then just store it away in the return type, and then it just lives in there. That's all that we do, right? Nothing more happens here. So let's look at the other role. Let's look at what happens from the awaitable side. So what an awaitable really is a type that provides the three functions: await, ready, await, resume, await, suspend, right? So we need to implement those three. So for now, in the await ready, we just say, okay, whenever ready, we really want to suspend. We don't quite yet know what to put in the await resume, because that is the function that will need to deliver the final result that the function was supposed to compute back eventually. But if we look at the await suspend and we look really carefully, we will notice something here, because there is a coroutine handle that's being passed here. But what is that handle pointing to, right? That's the handle to the coroutine that is about to be suspended as a result of awaiting on this async object. And that is the outer function handle here, right? So we really have two different handles here. The one that we stored at the creation of the async object, that's the one that's pointing to the inner object. But this now here is a handle to the outer function, which is the function that co-awaits on this object. So we also store this away. And if you now play this through repeatedly, right, you go to this little dance at different layers of always storing these two handles, and you draw a little picture of this, then you will get this, right? So each async object points to a promise, and the promise has a coroutine handle that points to its caller. And this is very similar to what we had before with our call stack. So we're up to something here. So the next question is now, I mean, okay, it's one thing to have this information stored away somewhere, but what we actually want to do is we want to resume the caller from a nested coroutine. So how can we do this? So assume you're the innermost function and you're done with all of your work, right? You have completed your result, and now you somehow need to wake up your caller, right? But your caller is not on the call stack anymore because everything was suspended, right? So how do you get him back? So we have the handle to the outer function, right? We saved that in our promise type. And now the question is like, how do we resume execution of that coroutine? So since the inner function has already completed, the way where we want to do this is in the final suspend, right? That's the customization point that will get called when the inner function reaches the end of its body, right? When it returns a value or when it falls off the bottom of the function. And now the final suspend allows us to return an awaitable that the compiler will then call co-await on. And that is the mechanism that we use here to transfer control flow. So I will just define this awaitable here at the bottom, which I call resume caller. If we look inside that, so remember we still have the handle that we want to resume stored away in the promise at the top. So in here we just say await ready false, like we're done executing and we want to suspend, right? The inner function doesn't want to go on. Await resume will never be called, right? The inner function is done. We just want to get out and want to get back to our caller, so we don't need to do anything there. And in the await suspend, we now return as a return value the handle to the outer function that was saved in the promise. And if you think back to part 1, we mentioned this in the very end. This is what is called symmetric transfer. This is a way how you can transfer control from one coroutine to the other. Similar to what we saw with the green threads in the beginning, where just like one thread suspended and then it swapped places with the other thread. This is a similar thing, only that the level of granularity here is always a single coroutine. So let's look at that in more detail to visualize this a bit better. So at the beginning, the situation that we have is we're in the inner function here, and we want to get back to the middle function at the top where the teal-colored arrow is. But that function is not on the stack, right? We only have like some base mechanism on the stack that is like part of the outer framework, and then we're in the inner function. So what happens is the inner function is done, right? So we call return value to handle whatever happens with the return value. and then we call final suspend, right? So we've now fallen out of the body of the inner function, and then we get to final suspend in the promise. This will now construct this resume caller awaitable, and then the language mechanism will call await suspend on that awaitable, and this will now return the handle to the outer coroutine. And now what happens, the part with the symmetric transfer, is notice how now we have the inner function on the stack, and it just changes places with the middle function, right? So here we had the inner function, and now it's not like a function call to the inner function, right? Because then inner would still be on the stack. It's like inner goes into suspension, it's now a suspended coroutine, it's paused, and it swaps places on the call stack with the middle function. And now the middle function resumes. So await resume is called on the awaitable. This takes care of like propagating the return value back out. And now we're back in the body of the middle function. It can continue moving on. It drops to the next line, and now what happens is, remember that the return value of inner function, that was actually the async object, right? But that was only a temporary on that line. So once we move to the next line, that temporary will get destroyed. And at this point now, the inner function goes away, right? Before it was just waiting in the suspended state, but now actually that we've moved on, now it actually gets cleaned up. So the order is a little bit different here, but the end result is still the same than what we would have in a normal function call. So again, here's the overview. The difficult thing here is really to keep track of like what is the context in which this async object is currently being used, and what are the different handles, right? The handle, what is the handle to the outer function? What is the handle to the inner function? And it's a bit hard to follow along with this if you just see it on the slides. But if you actually start writing code and you pay a little bit attention to this, I hope you will be able to figure it out rather quickly. Okay, so this gives us everything that we need to like resume from an inner coroutine to like its outer function. But we still haven't talked about like who resumes the innermost function, right? Somebody needs to start the chain, right? If we suspended everyone, then somebody needs to make the first resumption. Somebody needs to wake up that innermost coroutine. So how does this work? So I was being pretty hand-wavy before about what really goes on here in the inner function, but in the end, there is like some I/O framework, right? That you register with to say, hey, I triggered this I/O operation, and now I need to be woken up whenever that completes, right? And then like some machinery in the background will do like an epoll or a select, will eventually realize that, hey, this result is awaitable, and then that external mechanism needs to wake us up here. But for that to work, we need to register ourselves with that mechanism somehow, right? So what happens here is like this I/O awaitable that falls out of here, that is part of this external mechanism. But to construct this, we need to tell it like what to register with, right? So I call that the scheduler here. And the scheduler, that is really the entity that keeps track of all the outstanding I/O requests and what are the corresponding coroutines that need to be woken up when that result arrives. And the scheduler, like where does that come from, right? It's not anywhere in the function right now. So usually that lives at the level of main, right? So if you think about, if you ever work with Boost ASIO, you will have this I/O service, which you need to pass to all of the objects, because that's where they register themselves for the async results. And that usually lives at main, or at least fairly high up the call stack. So the easiest way would now be to just pass this down as an argument, right? So each function would gain a scheduler argument. But that's not very nice, right? So you will have this explicit argument everywhere, so your function signatures get blown up. You also don't really get any flexibility in changing this later, right? You need to know the scheduler upfront, and you need to propagate it all the way down, and it cannot change. So yeah, let's see if we can do better than an explicit parameter here. So yeah, how can we pass data from the outside in? So again, our point where we were establishing the links here was always the await suspend function. And we can really pass the scheduler along that same chain, right? So we have the link here where the right side gives us the context of the surrounding function, and any information that has, we can pass along to the inner function. One thing to watch out for here is that this promise type here that I have in red, because we're now having the two different contexts, like the inner and the outer, on the same line. If they have different return values, right? If the outer function has a different return value from the inner function, there will be different async objects, right? Since the async object is templatized on the return type. But since the promise type is a nested type of the async class, the promise types will also be different here. So that's a subtlety to watch out for. So really, this needs to be a different type. So we need to templatize it here. But we also don't want this to be an arbitrary type. We want this to be a promise that we know has a scheduler in there that we can propagate, right? So there's sort of this notion of a concept lingering here of what it means to be a promise that plays nicely with this mechanism. And hopefully someday we will get some advice from the standard library what we can do here, but not today. So far we need to figure this out on our own. Okay, so this now allows us to propagate a scheduler along, like from outer functions to the nested inner functions. But there's still a problem here, because if you think about, okay, like when do we actually need the scheduler? It's at this point where we've first reached the first asynchronous I/O call. But like this await suspend, when is that actually called? That is called when the outer function for the first time co-awaits on the async object that was returned here. So this has not happened yet, right? If we build up our call stack naively, as we would do in the synchronous world, at the point where we first reach this line, nothing has been propagated. The scheduler pointers are all null, and we don't know the handle to our outer function. So in order to avoid this problem, you really want to spawn all your tasks lazily. You want to make sure that before you first enter the body of the coroutine, all of the necessary information has been propagated. And this will now lead to a bit of a conundrum here, because it's very easy to just say, okay, then suspend always, everybody goes to sleep immediately. But then what happens is, okay, the outer function, it starts running, but then before it can do anything in the function body, it gets suspended immediately. But that's a bad point to suspend, right? We didn't do anything useful yet, right? We wanted to continue with the middle function. We wanted to get to the inner function where the I/O call happens, right? Because that's when we want to suspend, when we actually set up the I/O and we're waiting for the result. Suspending here is too early, right? So this also doesn't work. So what we need is sort of a middle ground here. And the way that this is done, and this is the most complicated thing here, so that's why I left it for last. So bear with me. In the await suspend, right? The await suspend is called on the awaitable of the inner function. It gets as an argument the handle to the outer function that is about to suspend now as well. Now, instead of just suspending here and going like even one layer further up, we're returning here the handle to the inner function, which means we're doing a symmetric transfer right back into the function that was suspended earlier. And let's look at this in detail, because this is the confusing part here. So I'm in middle function here, which is the inner function for this context. Initial suspend says, yeah, before you do anything, go to sleep immediately, right? We don't even enter the body, we don't do anything. So it goes away, right? We're back in the outer function. It now calls co-await on the async object that was just returned to it. It goes into await suspend. And then the await suspend returns the handle of the middle function. So we again do this symmetric transfer thing, right? So notice here we have the outer function, and now it goes away, and instead we get the middle function again. So the outer function suspends itself and then hands over via symmetric transfer to the inner function. And really, at this point, why should we stop at the scheduler here? So let's change this a bit and say, like, okay, all of our promises now inherit from a common base class. And in this base class, I keep two pointers, one that points outwards to the caller, and another that points to the child. And now in the await suspend function, I just establish the links in both directions. And now you can really propagate any data that you want along your async task stack. Because your call stack really now is just another data structure. And you control everything about that. So to give you one example of what the consequence of this is, because of the symmetric transfer that we're doing, right? You never get the full call stack with like outer, middle, inner function, right? Because as soon as you hand over, you do this little dance where the outer function is suspended and you symmetrically transfer to the inner function. So if you look at this in a debugger, you only see the inner function, right? And you don't know the context anymore in which it was invoked. And this is really painful for debugging. But your call stack is just a data structure. So what you can do is you can just write a data visualizer, and this takes you about 15 lines of NetVis code, and then there's your call stack in the data watch window. So yeah, I think this is a really useful way to think about coroutines, and to like inspire a little bit what kind of things you can do here and what kind of power they give you. Like, your call stack is just a data structure. You can resume, if you want to resume a function like higher up the stack, do some like exception handling kind of control flow where you just jump up further up the call stack. Sure, you can do that. It's just a data structure. If you want to splice two previously unrelated call stacks together, sure, go wild. It's just a data structure. You want to expose a range interface so you can use range algorithms that iterate over stack frames? Yeah, you can do that. But it's still, in the end, just the structure is still that of a linear list of nested tasks. So let's maybe do one more thing. Now it's a tree. Now it's a directed graph. I want to thank Louis Baker and Mateusz Pusch for valuable feedback on this talk and discussions that really helped me a lot in understanding this better. If you want to understand a little bit better how this works, feel free to check out the Got Bold example that I showed for the debug example in the end. It has like full working code here, and feel free to grab me in the hallway if you want to know more. And I'm happy to take questions also. Thank you. Thank you. Thanks.
Thank you very much. Please raise your hands if you want to ask a question. Okay, we have one here.
Hey,
Hey
thanks for the talk. Could you maybe tell a little bit about the application of the model that
Yeah.
this has been applied to? Because you said that the topic doesn't cover multi-threading, yeah? So if it's not used on multiple cores to handle the tasks, so is it just type of multitasking on one CPU and used for that? Maybe that's the case on the in the automotive or stuff like that.
No,
So
no,
I
no.
was just wondering.
Yeah. So the thing is, like, if you want to do asynchronous I/O, right? Most of the time, your I/O bound, which means you're just waiting for results, right? So your CPU is not busy doing like number crunching or whatever. It's most of the time you're just waiting for like the other server just to send your result back, right? And in those scenarios, you can get very far with just one core, since you're just waiting, right? And as long as you can manage efficiently having like hundreds or thousands of tasks up in the air that you're waiting for, you're fine with one core, right? But of course, if your load gets high enough, eventually, this alone is not enough anymore, and you want to use multiple cores as well. And then you can expand this mechanism to work multi-threaded in various ways, right? Like, sort of depends on your specific use case and how much you're willing to spend on like synchronizing between threads. So this is extensible to multi-threading, but it can be used, as I showed, also in a single-threaded way. So the decision is sort of up to you. And the only reason really why I didn't go into multi-threading is that it becomes much more complicated than it already is. So I wanted to leave that aside for another talk, maybe.
Yeah, sure, but your application was just like a one-threaded server that waited for the data or something?
Right, yeah, so like with this, you could have a server that just like accepts like hundreds of connections and then always waits for whatever result it needs from the other side, exactly. Yeah.
Thank you. Do we have another question, maybe? Okay, if not, once again, thank you, Andreas, very much.
Thank you all. Thanks.